Google is out with a new countdown that will excite the enthusiasts.
Google's quantum computing team has stunned the scientific world with an extraordinary claim. The James Webb Space Telescope may have captured evidence of a hidden dimension. Using cutting-edge quantum algorithms, researchers detected strange light patterns in deep space images that defy conventional physics. Are we witnessing a monumental discovery that could reshape our understanding of reality itself? Or is this just another cosmic mirage? The answer lies in the stars and quantum bits. The quantum breakthrough. What if JWST data just revealed a hidden dimension? Google's quantum computing team claims their algorithms have detected strange light patterns in deep space images. Patterns that might be the first evidence of dimensions beyond our familiar three. Stay till the end to see the one image that changed everything. The anomalies appeared in infrared data from galaxy cluster AEL 2744, showing subtle distortions that don't match any known effects. These aren't random artifacts. They follow consistent mathematical patterns that align perfectly with theoretical predictions of how extra dimensions might interact with our observable universe. Teams across the globe are diving into JWST archives with fresh eyes, using quantum and classical pipelines to reproduce Google's results. Observatories from ALMA to Hubble revisit same regions in radio, optical, and infrared, while university labs adapt quantum code for independent analysis. Shared datasets and forums speed debugging. Early signs hint that anomalies persist under varied methods, fueling cautious excitement as researchers race to verify these potential dimension clues. The breakthrough came unexpectedly. Google's quantum team wasn't specifically looking for extra dimensions. They were testing new quantum algorithms on astronomy data, hoping to detect subtle patterns that classical computers might miss. JWST's unprecedented infrared resolution made it the perfect test bed. When the first anomalies appeared, the team initially suspected instrument errors or data processing glitches. Only after months of rigorous testing and refinement did they begin to consider more exotic explanations. But what makes these supposed dimensional footprints so different from ordinary cosmic phenomena? And why did it take quantum computing to find them? The answers might rewrite physics as we know it. Could we be on the verge of confirming what string theorists have proposed for decades? JWST's cosmic window. The James Webb Space Telescope represents humanity's most powerful eye on the cosmos. Orbiting 1 million miles from Earth at the L2 range point, its 6.5 m gold-plated mirror captures infrared light with unprecedented clarity, seeing wavelengths that reveal what's hidden behind cosmic dust and gas. When pointed at Abell 2744, nicknamed Pandora's cluster, Webb captured the clearest images yet of this massive galaxy merger. The cluster's gravity bends light from distant galaxies behind it, creating arcs and distortions called gravitational lensing. These lensing effects should follow predictable patterns based on the mass distribution. But they don't, at least not entirely. Building on the excitement, new JWST campaigns will target suspected anomaly zones with multiple instruments. From near-deep imaging to near mid-infrared spectra, these sessions map light distortions across wavelengths, revealing subtle shifts in brightness and position. By repeating observations at varied roll angles, and surveying 4 core science themes, cosmic dawn, galaxy evolution, star and planet formation, and exoplanet atmospheres, they aim to confirm whether these curious blips signal hidden dimensions. JWST's technical capabilities make it uniquely suited for this discovery. Its primary mirror consists of 18 hexagonal beryllium segments coated in gold optimized for capturing infrared light. The telescope operates at temperatures below -370 degrees Fahrenheit, 50 Kelvin, necessary for detecting the faintest infrared signals without interference from its own heat. Its 4 main scientific instruments NIRCAM, NIRSPECM, IRI, and FGS NIRISS each provide different ways of analyzing light from distant objects. The telescope's position at L2 provides a stable environment free from Earth's atmospheric interference and thermal variations. This stability is crucial for detecting the subtle anomalies that might indicate extra dimensions. Even the slightest vibration or temperature fluctuation could create artifacts that mimic the signals researchers are hunting for, which is why JWST's extraordinary engineering is so important to this discovery. What makes these images so revolutionary isn't just their clarity, but their depth. Webb can peer back to nearly the beginning of time, capturing light that's been traveling for over 13 billion years. But could it also be capturing traces of dimensions we can't see? The answer lies in quantum computing's unique capabilities. Quantum computing's edge. Traditional computers, even supercomputers, process data linearly, analyzing one pixel at a time. Quantum computers work differently using qubits that can exist in multiple states simultaneously thanks to quantum superposition. This allows them to detect subtle patterns across billions of data points at once. Google's quantum AI team fed raw JWST infrared data into their newest processor running specialized algorithms designed to find correlations invisible to classical methods. Their quantum Fourier transform technique can simultaneously analyze multiple scales and dimensions, spotting tiny recurring patterns buried in cosmic noise. Even the most thrilling discovery can't escape the gauntlet of scrutiny. Instrument teams reprocess raw JWST frames, checking every calibration file for temperature drifts, cosmic ray hits, or electronics noise that could mimic distortions. Independent groups replicate Google's quantum routines, tweaking parameters to see whether anomalies persist. Theorists propose alternatives. Microle lensing by unseen stars, gas clouds, bending light, or software quirks in data compression. Workshops and online seminars buzz with heated debate, pitting cautious skeptics against eager believers. Only when multiple teams reproduce the same oddities under varied telescopes and methods will science ultimately give this hidden dimension idea rigorous, well-deserved credence. The quantum processors used in this research represent the cutting edge of computing technology. Google's latest quantum chip contains 72 qubits, each capable of existing in a superposition of states while still prone to errors and requiring extreme cooling to near absolute zero. These processes can perform certain calculations exponentially faster than classical supercomputers. The specific quantum algorithms deployed for this discovery belong to a class called quantum feature detection. These algorithms exploit quantum entanglement to identify correlations across massive data sets. In simplified terms, they can feel the entire dataset at once rather than examining it piece by piece. This parallelism is what enables the detection of subtle patterns that might indicate extra-dimensional effects. What makes these quantum algorithms so revolutionary is their ability to filter out the cosmic noise while amplifying subtle signal. But what exactly are these strange patterns they're finding? You'll be shocked when you see them visualized. The anomalous light patterns. But the patterns Google's quantum team detected show something different. Tiny kinks and ripples superimposed on the expected curves in the cluster's central region. Light from distant galaxies shows micro-distortions that repeat in a mathematical sequence. These aren't random. They follow precise geometric progressions that match theoretical models of higher dimensional space. When mapped in 3D, they create a pattern that shouldn't exist in normal spacetime. The most compelling evidence comes from comparing multiple wavelengths of light. If these anomalies were caused by ordinary matter or energy, they'd affect different wavelengths differently, but they don't. They show the same pattern across the infrared spectrum. Music, exactly as predicted if space itself has extra dimensions. When analyzed quantitatively, these distortions reveal fascinating mathematical properties. They follow a specific fractal pattern with a dimension of approximately 4.2, suggesting an influence from a fourth spatial dimension. The anomalies also exhibit phase coherence across different spatial scales. Another indicator that they might originate from extra-dimensional interactions rather than known astrophysical processes. The team employed advanced visualization techniques to make these subtle distortions visible to the human eye. Using false color mapping and contrast enhancement, they highlighted the deviations from Einstein's predicted lensing patterns. The resulting images show thin thread-like structures threading through the gravitational arcs. Structures that follow the precise mathematical signature predicted by certain extra-dimensional models. Could these patterns be explained by known physics? Scientists have ruled out instrumental effects, data processing artifacts, and conventional astrophysical phenomena. But before we jump to extra dimensions, we need to understand how such dimensions might actually work. And that's where string theory enters the picture. String theory's hidden dimensions. For decades, string theory has proposed that the fundamental building blocks of the universe aren't point-like particles, but tiny vibrating string. For the math to work, these strings need to exist in more dimensions than the 3 spatial dimensions we experience. Most versions of string theory require 10 or 11 dimensions total. Where are the extra ones? They're theorized to be compactified, curled up so tightly that they're normally invisible to us, existing at scales smaller than atoms. Imagine confirming hidden dimensions. This would spark a true paradigm shift, a fundamental change in how we understand space and time. Just as Einstein's relativity reshaped Newton's laws, evidence of extra dimensions would rewrite the rules behind every physics equation. The shock waves would ripple through science, transforming our models of gravity, matter, and energy. Textbooks would be overhauled, new research fields would emerge, and cutting-edge technologies might follow. What once seemed like wild speculation would become the new standard. In short, our cosmic playbook would flip open, revealing fresh chapters in humanity's quest to truly grasp the universe itself. String theory emerged in the late 1960s and has evolved through several revolutions into what theorists now call M-theory. A framework that attempts to unify 5 different string theories under one mathematical umbrella. At its core is the idea that fundamental particles are not zero-dimensional points but one-dimensional strings whose vibration patterns determine their properties. These strings are incredibly small, about 10 to the power of minus 33 centimeters or a million billion times smaller than an atomic nucleus. At this Planck length scale, the fabric of spacetime itself might become granular or foam-like with extra dimensions woven into its structure. According to string theorists, these extra dimensions could be compactified in complex geometrical shapes called Calabi-Yarrow manifolds.